Okay, good morning. I'm here. Yes, we may have some, definitely a question about the polar coordinates. Okay, we will see. Maybe we can find something about the polar bear. Okay, that means let's work on other shapes, and let's work today on the areas which is bounded by the polar curves. Yeah, the area of the polar bear. Okay, that means this was the last slide. This was the last shape that I introduced yesterday. We call cardioid because looks like a heart. Okay, and then it would be good if we will recognize the formula, which is, I can give you the general one in a minute, but something like 1 minus sine theta or 1 minus cosine theta or addition. It will always give us the same. I mean the shape, just different location. Okay, that means let's check the next one, because we do have a few other shapes. Okay, this is just my solution, step by step, how we can build. And that's the cardioid. Okay, another shape that we should also recognize is something like this. R equals to cosine 2 theta. That means the same thing. Instead of drawing a table and computing values and putting the values on the the polar plane, we will use the graph. Okay? That means this is the graph, just the regular graph like xy, cosine of 2x. Cosine of 2x is the curve that we have to squeeze two curves in the original period. That means instead of having one cosine, we have 1 and 2. Two cosine curves, because the period is pi. We have to divide 2 pi by 2 because of that coefficient. Okay, but this is just trigonometry. Okay, that means now we will see from 0 to pi over 2, this is the first quadrant. From pi over 2 to pi, the second, the third, and the fourth. Okay? And again, all of the y values, all of the height of the function represents the radii. Okay, and we will, all of these green lines, I will plot the same distance, but I will plot the distance like this way. Okay, like the polar coordinate way. And let's check what is the shape. One thing that we may notice, like from 45, I mean, actually, the multiplicity of 45 is giving me 0. That's 0, that's another 0, another 0, another 0. So probably it's worth to add the 45. That means this is 0, 90, 180. And I will also add a 45, because at 45, I have to come back to the pole, to the 0. Oh, that's the wrong line. No, that's correct, and that's correct one. Okay, let's start. For the 0 degree, the radius is 1. That means I will name maybe that value 1. And then what I have to do, I have to decrease the radius, the radii to 0. It means from 1 to 0. Okay? This is my, I mean, I don't have to really show the tracing. Do you remember for the parameters we have to, but maybe I will show it. Okay, now between 45 and 3 times 45, which is here, the values are negative. And if the radius is negative, we will not plot in the actual quadrant, we will plot in the opposite quadrant. That means for this quadrant, I mean half of the quadrant. For this one, this is opposite, right? And for this one, this is opposite. That means nothing at the moment, nothing here. Okay, and of course the distances are the same. That means from 0 to 1, but on the other side. from 0 to 1, and then from 1 to 0. Right? That means that's my shape. And then again, from 3 pi over 4 to 5 pi over 4, which is this part, I have to go to 1. We can see I'm here, 1, and then 0. Probably you see how nice flower we have. And again, between 5 pi over 4, this to the 7, everything is negative. Then I will plot in the opposite quadrant. It means from, something is wrong. That's not right. Because for 3 pi over 4 is 0. I think that's what I'm supposed to do. At pi is 1. Okay, that means this is my tracing. Okay, and then 1 to 0. And again from 0 to 1 at the 2 pi. Okay, that means cosine of 2 pi, we've got like a 4 loop flower or rose. Okay, but we have 4 loops. That means what is important to remember, cosine of n pi. Right? If n is even, we will always have double, the number of loops will be double. Okay? But if this coefficient n is odd, we will have the same number of loops, but still like a flower. Okay? And I can show you like in the difference. Let's see how our flower for sine 2 theta looks like. That will be exactly the same, but we know that sine function is shifted. That means we will shift to the 45. We will shift like 45. Okay, that's cosine, that's the flower. And sine of 2 theta. Oh, I have the graph. Oh, okay, I don't have I will draw it. And, oh, this is pi over 2, but we can see this one. This is 45, this is 3 times 45. And one sine and another sine. This is 2 pi, 3 pi over 2. 3, 4, 5 pi over 4, 7. But we can see the same, almost the same idea, but the zeros are at 0, pi over 2, pi, 3 pi over 2, and 2 pi. But the 1 values are at the multiplicity of 45. That means from 0 to 45, I have to increase the radii from 0 to 1. And then here, and I can possibly draw, because it's the same idea, the same flower, but on the 45. Everything should be nice and symmetric. Okay? That means, again, we have 2, the even number, the number of loops, double. If this will be odd number, like 3 pi or 5 pi, we will have the same number, 3 loops, 5 loops. And also, please notice that sine function, okay, sine function like sine theta, at 0 and at pi, 2 pi is 0. That means you, and maybe actually, yeah, 0 and pi, because the x-axis represents 0 degree and 180. That's the same. And we can see no points. It's just 0 for sine function. If I come back to my cosine, look at the cosine. Cosine at 0 and at pi, it's 1, negative 1. Okay? I mean, at pi is negative 1. Am I? Yeah, this is actually 2 pi. That means it's still 1. I mean, doesn't matter. We do have the values. We have a distance, 1 or negative 1. But what is important, we can see on the x-axis, we do have the value, because cosine at 0 is 1. That's how we can recognize the difference between sine and cosine. Right? Like sine and cosine, because For the sine, probably 0 will be always without the points. Let's look at this. Now we can see no points, just this one. We have no values like here or here. No, just 0. Okay, that means now what I have this few graphs, 1, 2, 3, 4, 5, 6, 7, 8. And maybe you will try to give me the formulas. All of them has these formulas, sine or cosine, and n is even or odd. Of course, we have to get which one. If number of loops is even, then we have to divide by 2, and this will be the coefficient n, because we remember, like, cosine of 2 theta, okay? Or sine of 2 theta. Number of loops will be double. That means maybe you can tell me number 1 and number 5. Which one is cosine, which one is sine? Number 1, it's definitely 1, 2, 3, 4. We just did. Number 1 is cosine because we can see on the 0 degree we have value 1, -1. That means this one is definitely cosine of the double angle because we have, two theta, because we double 4 loops. And this one is definitely sine of 2 theta because we can see no points on the x-axis, on the 0. That means if we have no points plotted on the x-axis, probably is the sine function. Otherwise, it's cosine. Okay, that means now, what do you think? I would like you to try to guess, educated guess. What will be the formula for number 2? Cosine or sine, first of all? What do you think? Cosine or sine? Definitely cosine, because we can see we have value 1. Cosine at 0 is 1. Cosine at 0 is 1. Cosine at 0 is 1. Now, sine at 0 is 0. 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 That means 1, 2, 3, 4, it's cosine function. Rest of them is sine. And now let's count the loops. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. This is 8. It's even. Then we have to write cosine of 4 because 4, we double 4, 8. Now we have only 3. And this will stay. If it's odd number, corresponds to the same. Odd number of loops will give me the same number of, the same coefficient. 1, 2, 3, 4, 5. Cosine of 5 theta. This is sine. Now, definitely sine, because no values on the x on the 0 degree. 1, 2, 3, 4, 1, 2, 3, 4, which is 8. It's 4 theta because we double, we got 8. 3 will stay, and 5 will stay. As we can see, as soon as we know a little bit of the shape, which corresponds to my formula, we can get the formulas. Yeah? That was nice exercise. So maybe I will ask you on the test to match the formulas to the graph. Okay, that's, we know heart, we know flower. Now let's look at this one. Sketch the curve, the polar curve, defined as a r minus 1, 2 sine theta. Okay, that means the same thing. I don't have the graph. It's okay, we can try to get the graph. Okay. First of all, I will draw a graph of the normal XY curve. So how can I draw a graph? This is 1 minus 2 sine theta. So I can maybe do this. Sine looks like that. Negative sine will be just opposite. So this is negative sine. Negative 2 sine will be like longer, right? We have to multiply each value by 2, but zeros will stay 0 because 0 times 2. And now the longer one, I have to shift 1 unit up. Okay, let me do it one more time because now we know what I'm doing. Actually, I don't need that yellow. Up. Okay, I will do, because I need I have to see how the radii will behave. Okay, that means this is 2. Okay, -2, +2. And now each point I will move 1 unit up. That means this will be -1, this will be 1, this will be 1, and this will be 3, and this will be 1. Okay, that means this is my final graph. That's 3. Okay, and we can put, this is pi/2, that's pi, that's 3pi/2, and that's 2pi. Okay, and I can even divide the quadrants. Okay, I have my first quadrant, second quadrant, third, and the fourth one. Interesting thing are the zeros. Okay? We have to know the zeros. That means function 1 minus 2 sine of x must be 0. Then sine of x is half. Sine for what angle is half? For pi/6 and 5pi/6. Pi/6, 5pi/6. Okay. I mean, what we need? We definitely need, as always, 0 and 90. I mean 0, 180, 90, 270. And I need this and this because this will be 0. Okay, and now my radius between 0 and pi/6, I have to decrease the radii from 1 to 0. Okay, from 1 to 0. Now, between pi/6 and 5pi/6, everything is negative. Okay, that means I will not plot any points here. I will plot them here, which I will probably need these lines as a supporting lines. Okay, that means from 0 to -1, which will be 1, and from 1 to 0. Okay, oh no, I will not do the tracing. Okay, this is 1. And now, from pi/6 to pi, it's 1. 1. And then from pi, can you see, from pi, I have to increase the radius up to 3. For 3pi/2 is 3. And then from 3, I have to decrease to 1. Oh, okay, a little bit more symmetric. Okay, I don't know if the shape looks good. Probably I have to be a little bit more rounded. This is almost the same shape like cardioid, but we do have a loop. Okay, and we call this shape, we call from the French, I don't know how to pronounce, limaçon. They also have a little like extra thing on that C. Okay, limaçon, maybe, I don't know. I don't really know the French, but that's the name of the shape. I will always call cardioid with the loop, yeah, because it's like the same shape like cardioid, but with that loop. Okay, that means what is important. Now we will change the position, and we know how to change the position. We can put upside down, we can put left orientated or right hand side orientated. And all of the variation is from this formula, 1 minus 2 sine theta. That's, of course, this one. 1 plus 2 sine theta. 1 minus 2 cosine theta. And 1 plus 2 cosine theta. I mean, all of them we will just rotate like 90 degrees. And let's see, that's 2. Oh, that's actually all of them, and we will match in a minute. Okay, but the general formula looks like this. A, the coefficient A, plus or minus coefficient B, sine theta or cosine theta. And now we remember, if A and B is identical, then it's the cardioid. Yeah? But if A and B has a relation that B is greater, which actually this means, if I multiply by B, if B is greater, which is this one, it will be always that cardioid with loop. Limason. Okay? We can see that if they are the same, it's the cardioid without the loop. If B is greater, it's the loop. Okay? And we can try to match 1, 2, 3, 4, A, B, C, and D. Okay, and okay, my screen now it's full. We just did sine. Okay, and also we can also think, because we're adding 1. That means cosine at 0. Cosine at 0 is 1. 1 plus 2. I mean 1 times 2 is 2 plus 1 is 3. That means probably the shape which is wider on the x-axis will indicate a cosine function. Something that is less wider on the x-axis is sine. That's when we just did this one, and this one was 1 minus 2 sine theta. This one will be 1 plus 2 sine theta. This one is 1, and because we have 3, that means this will be 1 plus 2 cosine theta, and this one is 1 minus 2 cosine theta. Okay. Am I right? Cosine is negative. Yes, that's actually correct. Yeah, but we can see, again, I'm just using the basic trigonometric values, the unit circle. Okay? But please remember the general formula and the relation between the coefficient A and B. We also have an extra, I will not go step by step, but you may kind of just remember these formulas. We kind of have like a r squared. That means of cosine of r squared equals to cosine of 2 theta, and r squared equals to sine of 2 theta. That means if we have square, we theoretically, if I will solve this for r, I only want this part to be positive. That means I'm removing, because these parts came from negative values. That means I'm removing the negative part. And the same, I did remove from that flower, I did remove the negative parts. That means if you see the square, it's only 2 loops of that flower and 2 loops of the other flower. Yeah? Just to remember this. Okay, and for example, you may see a question like this one on the test. And do you think you can give me the answer? We do have few students in the classroom. Which curve represents the curve 1 minus cosine of 2 theta? Yeah. B, definitely not this one, definitely not this one, because it's just the 1 minus cosine theta, 1, 1. Yeah? And I think this is, let's just double check, but I think, Joe, I think that's the correct answer. We can double check, and how can we check? If theta is 0 degree, cosine at 0 is 1, 1 minus 1 is 0, that we do have 0. Then 90, 180, 270, and 360. Cosine at pi over 2 is 0, 1 minus 0 is 1, and we do have 1. Excellent. And then pi is negative 1. Subtracting negative 1, we adding. That means this is 2. Really good. And then 3 pi over 2 will give me again 0, 1 minus 0, 1. 1, and then we will come back to 0. Really good. This is the correct answer. And you can see it's enough to just check the main axis. Okay, that's the nice and easy question. Okay, now we know all of the shapes. Oh, another one, which I probably copy from some of your assignments. Okay, which curve is this one? 1 plus 2 sine theta. Not this one, not this one, not this one, correct? Yeah, yeah, we did the minus, and we can see this one is wider on the x-axis. That means probably cosine is involved, something, right? This one is less, that means this one is the A one. Really good. I will remove this one. Yeah. Okay, nice and easy. Oh no, no, too much. Okay, I can just because we can skip this one. You can probably practice, but my point was that to show you that we don't have to have 1 and 2. We may have like 2 minus 4, but still it's the same shape because coefficient B is greater than coefficient A. That means will be the limaçon, the cardioid with the loop. Yeah? But we know that's sine, that's cosine, and that's cosine, and you can figure out which one. I will skip this one because we do have some symmetry, but it's obvious. Okay, that's we know all of the shapes. Okay? We know circle, we know cardioid, we know a flower with even number of loops or odd number of loops, and we know cardioid with the loop, limaçon. Okay, now we will try to find a few areas. Let's see the formula. First of all, let's try to recall a formula for the sector of the circle. And that's the formula, hopefully we remember, 1/2 r squared theta. Because when we have the whole circle with the radius r, do you remember the formula for the area of the circle? Probably it's nice and easy. Are you typing? Pi r squared, right? And this kind of represents the angle, I can say. But for the full revolution, we do have, no, okay, it's easy for me to write down, yeah, no, I know that you know, everybody knows pi r squared. Okay, but what I'm trying just to show you a kind of like a sense of that equation. Okay, that means the whole circle, the area is pi r squared, but in fact this corresponds to the total angle 2 pi. Okay, now if I will take half of the circle, okay, half of the circle, the area will be pi r squared over 2. Just half of them. But half of the circle is just the angle pi. Okay? And maybe a quarter, because then we will see quarter corresponds to 90. But a quarter, it's simply pi r squared over 4. That's what I'm trying to find the general formula if I will have any sector with the angle theta. Okay? Because what's happened? If the full revolution corresponds to 2 pi, we do have half of this, right? Pi, half of this. Pi over 2, half of this, pi over 4. Then, if I have any angle theta, I have to divide by 2 and keep my r squared. That means this is the area of the sector of the circle. And this is like that, we just switch the order. 1/2 theta r squared. Okay? That means having a theta and radius. Okay, that means we have to remember this. And now, what we will do? We have this region bounded by the polar curve. Okay? From A to B, the angle and the curve. And we remember, right, we remember the calculus 1, we remember the definition of the integral, finding the area under the curve, we were using the rectangles because we were approximating the area of one rectangle and then we add all of them together from A to B. And we did have infinitely many of them for the perfect approximation. and adding infinitely many areas, this is the integration. That means we will definitely integrate, but since we're not using the xy coordinates, we don't really have like a perpendicular, like xy, like length, height, length. We will divide this region by the sectors. That means, let's see. I will divide, like kind of like slice it, but of course the angle way, that the whole region, and I still don't like everything. It's not right. I mean, the side is a little bit like skew. It's not really, yeah, the nice circle one, okay? But doesn't matter. Each of this sector I will approximate as a sector of the circle, and then adding all of them together. And we know that the perfect approximation is if I will have infinitely many of them, which will be the limit, because if the infinity is involved, we have the limit notation. Limit of the sum is, of course, the definite integral. That means, one more time, finding just the area of one of the sector, I need 1/2, okay? Radius, we remember the area of the sector was 1/2 radius squared and theta. It means I need 1/2, and the radius, of course, this is my function. Radius will be defined as a function. That means this will be 1/2 function, okay? And the theta, which means is that thickness, delta theta. That means this is the area of one sector. Now we can see 1/2 r squared theta, d theta, and this is just one. If I want the perfect approximation, I need infinitely many of them, and as soon as I see limit of the sum, this is the definite integral. Yeah, that's the definition. It means now, to make the nice summary, in order to get the area of the region bounded by the polar curve, I have to integrate the area of the sector, 1/2 r squared d theta. Of course, d theta, it's telling me that I am integrating with respect to theta. I'm like slicing the angles between A and B. And radius is defined as a function, yeah, in terms of theta. Okay, that means just 1/2 radius squared d theta. Okay, that's pretty much everything. Let's just solve a few problems. Yeah, that's a little bit maybe more clear. 1/2 radius squared d theta. And hopefully the radius will be provided. I mean, the formula for the r. One thing, because we may have the area between two curves, but we will apply the same method that we did in Calculus 1. We will simply subtract. Okay? We will subtract the longer radius from the shorter one, and then we will have the distance between, which means 1/2 r squared d theta minus 1/2 r squared d theta. But this is the upper one, the longer radius, we can see, and this is the shorter one. Because from the longer, subtracting the shorter, I have the stuff between, the region between. Okay, that's we can see. But still the formula of the sector, of the area of the sector of the circle. 1/2 r squared d theta, 1/2 r squared d theta, and everything from A to B. Okay, let's do the first one. Find the area enclosed by one loop of the 4-leafed rows. Yeah, we may call this curve this way, r cosine theta. That we can nicely see the graph, but we just need one loop. We know that this is 45 because the limits of integration are so important. Oh, okay, I didn't. I mean, what I need my formula 1/2 r squared d theta from A to B. And I can say from negative pi over 4, one loop, to pi over 4, I can place 1/2 outside, and r is actually just given, cosine 2 theta That's my r, n squared. Okay, that's almost everything. But what we will expect from you, we will expect that you will use a symmetry. You can definitely see that that loop is symmetric if I will divide using my 0 degree, my x-axis. So I can set up an integral just from 0 to pi over 4, and it's the same thing, 1/2 r squared, which is this one, and I can multiply by 2. Okay? By 2, because then I have 2 of those, but they are identical. That means probably on the test, this will be the option. Of course, 2 times 1/2 is gone. No 1/2, no coefficient, just simply 1. And then r squared, cosine to theta squared. Okay? And I believe I solve it for you. Yeah, you can see this. That's what I'm looking for. We still have to know how to integrate, but this is more section 7.2, I believe. Okay, to integrate cosine square. For me, the concept is important for today, and that's the integral. Because most likely for this section, we will ask you to set up an integral. Yeah, like not evaluate the integral. You may have this question, but totally different, yeah, not related to area. Okay, let's try this. Find the area of the region that lies inside the curve 1 plus sine theta, and outside the curve r equals to 1. That means I did start drawing. This is, we know that this is cardioid. And you can check sine at 0 is 0, 0 plus 1 is 1, and then 2, 1, and then 0. That means that's the shape. That means this is my first curve. The second curve, it's just the circle with center 0, 0 and radius 1. That means I will try to draw it. Okay. And now we're looking for the region inside cardioid and outside a circle. This one. Okay. I mean, I will have an area, an integral of the longer, right? The longer radius. That's longer, that's shorter. That means I can possibly name this 1 and this 2. R sub 1 minus R sub 2. Oh, no, wrong. I have to be careful. Let me simplify. I mean, not simplify. 1/2 r squared, 1/2 r squared. This way. Because otherwise we can make a mistake. Okay, because I have one sector minus another one. Sector with the longer radius, which I named this one, the cardioid. Okay, and this is just this one, the shorter radius. Okay, now I can put 1/2 outside. The longer radius is 1 plus sine theta squared, and this one is just 1 squared. I can keep that square for now. And my limits of integrations are from 0, because we can see the graph, to pi. But what we will do, we will use the symmetry from 0 to 90. Okay, from 0 to 90, longer radius minus shorter radius, of course, squared, and 2 times half. Let me use that for the symmetry. That's the first part, and that's the second part. Of course, again, 1/2 times 2 will be gone, but remember about this. Okay? And that's what we're looking for. Nice and easy. Okay, let's try this one because we don't have any picture. Find the area of the region that lies inside a circle 2 times cosine theta, and outside, again, r equals to 1. Do I have any graph? Oh, no, I don't. I have the graph for the next one. Okay, that means I will draw 2 cosine theta, we remember, is a circle in the first, I don't know if that's circle, probably not, in the first quadrant and the fourth one, because cosine is positive and the diameter will be 2. This one is 1 with the center 0, 0. And let's check. Inside cosine and outside, that means is that part. 1, 1, 1, 1. Okay, we definitely, for this one, we definitely need points of intersection because this will be my limits. Let's say theta 1 and theta 2. We will still use the symmetry. You can see I can actually apply the symmetry right away because in order to get an area, I will integrate from 0 to that angle, from 0 to theta 2, 1/2 r squared minus 1/2 r squared. And one of them is longer. That means longer is this one. I can name maybe 1 and 2. Longer is cosine. That means this is my longer and this is shorter. Okay, I can put, and actually I did put 0. That means I will multiply everything by 2. Let me use the Bluetooth. Okay. Right, because you can see my limit is 0. That means 2 times 1/2. 1/2 is outside. Longer is 2 cosine theta minus 1 again. Okay, but I need my angles. What I have to do? I have to find the points of intersection. 2 cosine theta is equal to another curve 1. Cosine theta, it's 1/2. Cosine for what angle is 1/2? Of course, for 60 degrees. That means this is pi over 3. And this is negative, but we will not use it. Pi over 3. Oh no, everything has to be boxed. Okay, and again, this will be, that's gone. Okay, that means make sure that we know the shape, we know the points of the intersection and the formula. And no integration required for this section. Okay, let's do maybe 1 or 2 more. Let's see, I have this one, but you have the, or maybe, okay, I have 2 multiple choice, 1 and 2. Yeah, okay. Let's solve those and we will be done. Set up but do not evaluate an integral expression for the area inside the curve 1 plus sine theta and outside the curve r equals to 3/2. Okay, similar, we just did it almost. I will draw it first. Okay, this is definitely the cardioid, right? That's the cardioid. And sine at 0 is 0. That means we will have 1. And then sine at 90, we will just do at 0. Sine at 90 is 1, 1 plus 1 is 2. Okay, that means I know my shape because I just need, okay, not bad. Now the curve is 3/2. That means the radius is a little bit bigger than previously. That's 3/2. And I want this to be a little bit more symmetric. Okay, better. And this is that region. Of course, I will use symmetry. I need points of intersection because this is happening from here to here. Theta 1, theta 2. It means my area is defined as an integral from theta 1 to theta 2, 1/2 r squared. r squared minus 1/2 r squared. But let's fix it. I need the longer one, which is the cardioid, and the shorter one is the circle. I will apply my symmetry, multiplying by 2, and the symmetry means that I will only focus on this half. From θ1 to pi over 2, I can place 1/2 outside, and the longer radius, it's 1 plus sine theta, and circle is the shorter one. Oh, I did put the bracket. Now I only need this, that means point of intersection. 1 plus sine theta must be 3/2. Sine theta is 1/2. Sine for pi over 6 is 1/2. That means this is pi over 6, and this will be 5 pi over 6. But we not need this. Not 5 pi over 6 only. I can write this down, but we're not using this. Okay, that means this is my final answer. And I see from pi over 6 to pi over 2, cardioid squared minus 9 over 4, and no coefficient in front because 2 times 1/2 is gone. Okay. And let's do one more, and we have lots of practice in this session. Let's try to figure out this one. Which integral represents the area that lies inside a circle, right? 3 cosine theta, and outside the cardioid? Let's check. We will find the points of the intersection, but it's nice to see the situation. In what we will have, this is definitely a circle. Okay, let me start maybe with the cardioid. This is cardioid, but what is the position? Cosine at 0 is 1. 1 plus 1 is 2. Okay. And then cosine at 90, cosine at 90 is 0. 1 plus 0 is 1. Okay, that means I have to go to 1. Okay. I just like the nice, okay, that's 1. And then cosine at pi is negative 1 plus 1 is 0. And then, okay, is this position? No, that's not pretty. Let me just draw it. Okay, not bad. This is 1, this is 1, this is 2. Now, this is a circle with the diameter 3 in the first and the fourth quadrant. Okay, good. And we looking for the area inside the circle and outside the cardioid. We need points of intersection. That's the points of intersection. Let's say θ1 and θ2. But I will definitely use the symmetry. I will integrate from 0, okay, to θ1 only. It means my integral, which represents the area, is from 0 to θ1, we will find 1/2 r squared, 1/2 r squared. But we need the longer radius, which is in this case, it's the circle. That means this is the first one, this is the second one. First one, second one. I will put 1/2 outside from 0 to θ1. The first one is 3 cosine theta, and then 1 plus cosine theta squared, of course, d theta. Let's find a point of intersection. Probably you see the answer right away. Yeah, it's D, because D is good Okay, we just have to figure out if it's pi over 3 or pi over 6. I believe you're right, but let's just quickly do 3 cosine theta must be the same like 1 plus cosine theta. Solving for cosine, we will have 2, 1, 1/2. Yes, cosine for 60 and for negative, yeah, I can use the negative notation. But that will be negative, and this is actually what we're looking for. That means this is definitely the correct part. The only thing is, since I actually missing something, this is 0, I have to multiply by 2. Shall I use my blue color to be consistent? I'm multiplying by 2 because of that 0, and because it's just half and I have to cover everything. Okay, that means that's not a mistake, this is the correct answer. Okay, I will put my video on. Okay, that means that's the problems, and you can only expect questions like this one. Okay, that means make sure that you know all of the shapes and the area of the sector, which is placed in the definite integral form, because we need to integrate, of course, application of integrals. Okay, that means that was actually the last session with the new stuff. Next week we will have just the review session, the final exam review session, okay, which you can see probably lots of materials on Canvas, and you can definitely start practicing, but I will run the review session and I will give you some important information and some tips. Okay, thank you very much, and enjoy your last section in this Calculus 2 class. Okay, thank you. Thank you very much for the participation, and thank you for joining me for the live session. That's really, really nice. Okay, thank you.